All right, so we'll get started here. So continuing our story about topology on the complex numbers, this is basically, we're just setting a language so we can describe the shape of sets. And so here's some terminology. If we have a subset of the complex numbers called S, all right, then y an element of the complex numbers. Notice that y is not necessarily in S, all right? Well, that's called a limit point of the set S if the ball of radius epsilon centered at y, the disk of radius epsilon centered at y, right, intersect with everything not including y in S is non-empty. S is a set of complex numbers. So here's a picture of S. Suppose S is this, as well as this. All right. So the limit points, and I'll try to shade it here. So my S I have in mind here at the moment, I have attempted to draw on the board. So I'm trying to say S includes all of this. All right. So this is filled in. You can see the edge of it I wrote in white. The dotted line indicates that those points are not in S. But as you can see, we've got these points over here which are in S, all right? So I'm saying suppose S is all of this. All right? What are the limit points in S? Well, the limit points means that, remember what d epsilon of y is? This is z in the complexes such that the modulus of z minus y is less than epsilon, right? In other words, if this is y, then this is the open disk centered at y, right? It's this. Okay. Now, so what are right? Not including the the edge of it. Not including the boundary, actually, right? The boundary of the disk of radius epsilon, of course, would just be the circle of radius epsilon centered at y. So what are limit points of S? Limit points of S include all the points in the interior of S, right? So like this point right here is a limit point, right? Because it doesn't matter how big the ball of radius epsilon you build around it, the intersection of that with the set excluding y is always non-empty, right? So that's a limit point. What else is a limit point? Any of these points on the edge are limit points, right? Now, a boundary point is a point that every open disk, right, like here, is a boundary point because any open disk I take there, there's points outside of the set that makes it a boundary point. So you pretty much have an intuition for what the boundary of S is, right? Like the boundary of S includes, of course, everything I've drawn in white as well as the dotted region, right? That would be the boundary of S, as well as these three what are called isolated points over here, or exterior points. They're isolated because there exists an epsilon greater than 0, right, like this one. See, I can draw this open disk around that point, and the intersection of that disk with that point is just the point. There's no other.
Yeah, because that's not
right.
S.
But notice it's a there exists statement, right? If I made epsilon big enough, then I'm going to cut into all of these things, right?
Oh, yeah, so you actually wouldn't have the entire.
So boundary point is every disk contains points inside and outside. But the isolated point is there exists a disk that isolates it from the set. Interior set of all interior points. Remember, interior point is one which there exists an open disk around the point centered in the set.
Is there a limit on how big this disk, or it can be infinite?
Can be infinitesimally small, yeah. I mean, it has to be a finite radius, but no matter how close you get to the edge, you can always You know, now these points are not interior points because you cannot fit an open disk
Yeah.
around there that is inside the set. In fact, that's why it's a boundary point,
Yeah.
right? So what I'm
Isolated points outside of the set. Boundary points, you can't make a circle big enough or small enough to where you won't hit something outside.
right, right.
Boundary just means something's outside.
Yeah, any boundary point means any open disk that you take around that point, there's points inside and outside. So
Isolated point, only one.
only one, yeah.
Gotcha.
So, but the closure, so the limit points here include what? Include the interior points as well as the boundary points. All right. So they call that the closure, right? The closure of a set. You take the set, union all its limit points. This is the so-called closure of the set. The closure of a set is a closed set. In fact, it's the smallest closed set, which includes the set as a subset. You could take the closure to be the intersection of all closed sets which contain that set.
But the limit points again are just any point that when dist gives you like every point in the set.
The limit point is by definition every open disk
Every open disk.
intersect with everything except for the center of the disk
Uh-huh.
is non-empty.
Okay.
Another way you could write this would be that the intersection of the deleted open disk centered about Y intersect with S is non-empty. So if the limit point, if every deleted open disk around the limit along the alleged limit point is in fact intersecting the set.
So yeah, so the point closest to your little marking at limit point.
Yeah.
A little farther down, boundary point.
So
Isolated point.
the closure of S, you notice we can take it, basically it's the interior of S union with the boundary of S. All right? All right, enough about that. So again, this is mostly just language for us. Definition. Z1, Z2 is equal to, let's see here, Z1 plus T times Z2 minus Z1, such that 0 less than or equal to T less than or equal to 1 for any Z1, Z2 in the complex plane. This is the so-called directed line segment, the directed line segment from Z1 to Z2. So we're generalizing interval notation a bit, okay? But that's just, this, you should recognize this is just the formula for like parametrizing a line that goes from Z1 to Z2. If you plug t equal to 0, you get Z1. If you plug t equal to 1, you get Z2. And as t varies from 0 to 1, you get the whole deal. Furthermore, although this is kind of funny because in retrospect, you know, in pre-calculus, I make fun of students if they give me like the interval from 4 to 3. Mm-hmm. But with this notation, it makes sense. It's just it goes from 4 to 3, you know. So although this also agrees with interval notation as we commonly use it in the reals, as much as you look at directed line segments along the real axis of the complex plane. All right, definition. U, a subset of C, is star-shaped. All right, with star center Z naught, all right, if there exists Z naught in U such that each Z in U has the line segment from Z naught to Z a subset of U. And the star center need not be unique.
Is star shaped like
It's a stronger form of simply connected. See, because, like, of course, you could have something like that's literally, you know, like a star, and then, you know, there's your star center, because no matter where you go, see, you can reach anywhere in the set from that star center, right? Another example, the slit complex plane, right? So you deleted the negative real axis. What's the star center here? Well, you can make the star center any point, like over here. Because you can reach any point in the slit complex plane by line segments based on that point. You just can't hit that. Of course, the complex plane itself is star-centered. You can take any point as a star center because you can take a line segment from one point in the complex plane to any other one. So lots of sets are star-centered, or star-shaped, rather. Next up, what's a polygonal path? I sometimes call these piecewise linear paths. Definition, polygonal path. All right. We could call it gamma from A to B in C. It is something like this. Gamma equals to, what you do is A1, A, Z1, union Z1 to Z2, union Zn minus 2, Zn minus 1, union Zn minus 1 to B. A. So here I'm saying Z0 equals to A and Zn equals to B. But basically, a polygonal path, you've got your point A, you've got your point B, right? And you're doing one of these deals. You know? So this is what a polygonal path looks like. It's just a finite union of directed line segments, right? Definition. S, a subset of C, is connected, all right, if and only if there exists a polygonal path between any given pair of points in S, and let me call that path gamma, and gamma is a subset of S. All right. Definition: an open connected set is a region. So region is a technical term in this course. Region means open and connected. All right, open means every point's an interior point, and connected means any pair of points in the set can be connected by a polygonal path. And we say R is a region. Oh, did I say region? I meant domain. I'm an idiot. Golly. Domain. My bad. So sorry. Oh, domain, open connected set. Idiot. What's a region? R is region if R can be written as the union of D with S, and D is domain. And S is a subset of the boundary of D. So much writing. Not a lot of calculations to learn here, right? Just a lot of terms. Because we need these terms. We're going to say, consider a domain, consider a region. As we go on in the course, we need to have these terms have meaning. But really, we're just giving a vocabulary lesson at the moment. And let's see here, another definition. U, a subset of C, is bounded if there exists M greater than 0 such that, well, no, excuse me, that's not the right way to say it. If there exists epsilon greater than 0 such that U is a subset of the ball of radius, I'm sorry, why not? And why not an element of C, all right? If there exists a point in C and a radius epsilon such that U fits inside a disk of radius epsilon, centered at why not, all right? If U, a subset of C, is closed and bounded, then U is compact. So compact means closed and bounded. All right? All right, so some pictures here. So if my set looks like this, right? This is not connected. See, because in order to take a polygonal path between this point and this point, right? What do I have to do? Yeah, I have to go outside the set, right? Not connected. On the other hand, if I had the set like this, this would be polygonal connected. See, because I can take any point here, right? And what can I do? Any point over here. Of course, you can connect any point in the two little blurbs I just drew here. But so what you can do is just kind of go like this, right? And then follow that line segment, and then follow that line segment, and then follow that line segment. So there you go. That's a polygonal path, which is a subset of my given set here. So I'm trying to make this set the shaded in version with these two kind of line segments connecting them, yeah?
Okay. So the first one isn't packed.
Isn't connected.
Connected, sorry.
They're both compact.
But why couldn't you go out the set in the bottom one and not the top one?
So these are both connected because in both of these cases, I have not drawn a fuzzy edge. And if you look at, if this is S, you can notice that S is equal to the closure of S.
Yeah.
And likewise, this one down here, S is equal to the closure of S. Because if you take the set union with its boundary, it's still the same set. So these are closed sets, and they're compact because they're finite, which means I can take a big circle and close them, you know. So they're both compact. The first one, So this is not part of the set, right? This is just my attempt to show you what the problem is. I can't draw, and I mean, of course, I should just try to connect A and B directly, right? I mean, that's the first thing you try to do, and you can't do that, and it doesn't matter like how you bend it around, you're stuck, you know, because you're outside of S. You can't keep the polygonal path inside S. So it's not connected. This one is connected because even though these are two kind of disconnected, if you will, in the usual sense of the common sense of the terminology, but they are, see, they're not really though, because there's this linkage that I'm drawing as part of the set, right? This white, this is part of S I'm giving.
Oh, okay.
And my point is you can follow that link to connect them. In fact, like here's a more general thing, like if you have this as a connected set, right? And this time I'll make part of the edge bounded. And then I have one point, right? One point, which connects it to another connected set, right? If there's just one set, one point which connects them, then the union of both of them is still connected because you can just, you know, take the line segment and run it through that connecting point to connect any 2 points in the set. So, all right.
Okay, but for the bottom one, that's actually white and orange. That's why
Yeah.
I'm thinking that.
Right, yes. The orange is my polygonal path. To be consistent in my color coding, here's the orange. All right, sorry. If I was using the whiteboard, we might have better success with this. No? Okay. Great. Region. So like, what's a region? So region basically means if you take something like, I don't know, whatever. So this is connected. Right, this is, if I shade it in, this is a connected set, yeah? But it's not a domain because it's not open, right? The points on the solid part of the edge, they're what? They're, you see, they're, you know, they're not interior points, right? Like this is not an interior point. So this is not an open set. However, this is a region because it is clearly the union of the domain which you get from just fuzzifying the edge, right? And you take that and then you union with just this part of the boundary, right? So you don't have the whole boundary, but you got at least a part of the boundary, you know?
Yeah.
So that's a region. The larger point is here in both a domain. Well, in a domain, every point in a domain is a limit point. In a region, the interior of the region, every point's a limit point, right? And that means we can take limits at those points. Because if you look at our definition of limit last time, it basically presupposes that you've got a limit point. That's why they're called limit points. You can take limits at them. I mean, that's one way to think of it.
Domain, every point is a limit point.
That is true.
Region, every interior is a limit point.
Right. Now,
Oh, that's essentially saying that the domain is like, how do I say this? It's really big. So if you could never get outside the domain, whereas the region is like, oh, I'd let you know.
I think of them as the same size. The question with a domain's got a fuzzy edge if it's finite. A region can have partly, it can either have a completely solid edge or it can have a partly solidified edge. But we can also talk about like infinite domains and regions, and so there are some of my, like the upper half plane where the real axis is not included is a domain. But if I say the upper half plane with the real axis included, the positive real axis included, that would be a region. Because it's got part of the... Anyway, we will continue to use these terms and reinforce them as we go on. Finally, theorem. If h, which is a function of x and y, is continuously differentiable on a domain D, which is a subset of the complex plane, which we think of as R2, all right? such that the gradient of h, which of course is what? Partial h, partial x, partial h, partial y. Remember our Calc 3, yep. And that's equal to 0 on D, then h is constant. Here's the proof. So we've got a domain, right? We take a point. I mean, it doesn't have to look like this, right? It can be more complicated, right? Whatever. We've got a point A. We've got a point B, right? Because it's a domain, it's a connected set. So given that pair of points, A and B, we can connect it with a polygonal path, right? So gamma is the polygonal path which connects it. So in particular, if we look at, say, the line segment from, let's just focus our attention on the first one. So like from A to Z, I'll take the second one, from Z1 to Z2, all right? Then from Z1 to Z2, what do we have? Z1 plus T times Z minus Z2 minus Z1. This is a parameterization. I'll use alpha for a second here. Alpha of T is the parameterization of the line segment which goes from Z1 to Z2, right? So here's the point, alpha of T, somewhere in there, right? And that's, of course, for 0 less than or equal to T, less than or equal to 1. Okay? Now, we can take the derivative of the composite of H of alpha of T. So H is a function, right? H is a function from the complex plane, right? We could take it to be a real valued function for the moment, if you like. Let's do that. And then what we learned in Calculus 3 is that we have a chain rule. Yeah. And the chain rule can be written like this. It's the gradient of H of alpha of T dotted with d alpha dt, where that's the dot product. This is the chain rule. But we know that the gradient is 0 on D, right? So certainly the gradient restricted to the line segment Z1 to Z2, which is a subset of D, is 0 as well. So this is 0. So this is 0.
And why? And 0 again, why? On the first one?
We're assuming it's given that the gradient is 0.
Oh, okay.
So if the gradient of the function is 0 on a domain, which is an open connected set, we've just shown that h of alpha of t is 0, right? What does that mean? That means that h of z1 is equal to h of z2. See, because alpha of 0 is z1, alpha of 1 is z2. But you can see that this argument equally well applies to any of the line segments forming the polygonal path, right? So that means that the function at the start is equal to the function at the first linkage, at the second linkage, all the way out to the nth linkage. But we've just connected the value of h at A to the value of h at B, and they're equal. Therefore, h is constant on a domain. So our first actual theorem. What I have written in the notes is slightly less sketchy, but that's it. All right, good. Now,
Wait, what? Oh, yeah.
did I move the camera back? I think I did. All right, so now, finally, I am done with what I was supposed to cover last class. Here we are, a half hour in. Sorry about that, but I always forget how long it takes to really say these topological things. There's really, I really don't feel like there's a lot to it. It's really just a language, right? But
Yeah.
we do need this language, so when I tell you, we're working on a domain or we're working on a region, we know what that means. And star-shaped is also critical to a lot of theorems later. We'll prove theorems for star-shaped regions because it's a convenient description of their shape and the fact that, anyway, certain proofs are easy for star-shaped regions. There are always like harder versions of those proofs for like simply connected. But anyway, here we go. So section 2.2. Now, Gamelin has entitled it analytic functions. I really don't care for that. So I'm going to talk to you about complex differentiability. So I really think that Gamelin's use of the word analytic is not best in this book, to be honest. So I don't really follow him in that regard. Okay? Here it is, definition. If the limit as z goes to z naught of f of z minus f of z naught over z minus z naught exists, then f is complex differentiable at z naught, and f prime of z naught is defined to be that limit. I'm just writing the same again, but sorry, it got lost in the bump there. Furthermore, the mapping z maps to f prime of z is the complex derivative of f.
So it looks like it goes without showing this continuous in R continuous in Z, but not vice versa.
Continuous in R, continuous in z. I don't know what you mean.
Like if we have a differentiable function in R, it should be differential over the complexes, but not vice versa.
Oh, I haven't really defined differentiability over R. We will talk about that, but not today. This is actually a stricter condition than that. This much is true. Z naught needs to be a limit point of the function, so we can take this limit. But of course, just like in the real case, the difference quotient is what? It's type 0 over 0, if supposing f is continuous, and that still means what it meant, which is the limit is z goes to z naught of f of z is equal to f of z naught. In fact, if you look at the epsilon delta definition that I rattled off last class and sort through it, it does imply that. Okay, so this is really just calculus 1 all over again, right? We're defining the derivative by the difference quotient. We can do that because in the complex number system, every non-zero thing has is reciprocal, is defined, right? So it's sensible. And the question is, what can we prove about this complex derivative? All right, so I'll give you a little more terminology. If f prime of z exists on some, let's see here, uno momento. I give this terminology at the very end of my section, but I think I don't want to bury it in today's lecture. This is actually definition on page 33 of my notes, definition 2.211. If f prime exists on for each z in D a domain, all right, then f is holomorphic on D, right, and f is holomorphic at z naught, all right, if there exists open disk on which, open disk centered at z naught on which f restricted to D is holomorphic. All right, so what am I saying? I am saying that holomorphic at a point means that it's differentiable, it's complex differentiable, not just at the point itself, but actually on some open disk centered around the point. And then we say it's holomorphic on a domain if it's holomorphic on at each point in the domain. All right, so complex differentiability is at a point. If we have complex differentiability on some open set centered at on some open disk centered at the point, it's said to be holomorphic at that point. Right? So f restricted to D, the function restricted to D. Okay, so how to prove theorems about complex derivatives, right? How do you do it? There are different approaches to doing this. The one approach, which I don't take, but I think Gamelin does, is to just pretty much recycle the arguments from Calculus 1, right? So, and tell you what, I'll do that once. Okay, so we could theorem ddz of f plus g is df dz plus dg dz, you know? We could prove that. And the proof could, and assuming, of course, that assume f prime of z and g prime of z naught exist, yeah? And then you can look at the limit as z goes to z naught of f of z plus g of z minus f of z naught plus g of z naught, right? Parentheses over z minus z naught. This is the difference quotient for the sum of the two functions. So that gives you f of z minus f of z naught over z minus z naught, right? Plus the limit as z goes to z naught, g of z minus g of z naught, z minus z naught. But those limits are given to exist because we assume that f is differentiable at z naught and g is differentiable at z naught. So those are respectively f prime of z naught plus g prime of z naught. Right, so therefore, f plus g prime of z naught is equal to f prime of z naught plus g prime of z naught. So there you go, we have proved the sum rule. This is the calculus 1 argument. We just deal with the limit quotient directly. But there is another way to look at differentiability, which is actually very beneficial and is making proofs much easier. And so I will share that with you. It's the theorem of Caratheodory. All right. So I'm going to state it. So another way to look at this is what I'm about to write down is another characterization of differentiability. You could take it to be, you could in some sense use this as a definition of complex differentiability, but anyway. So Caratheodory. It says this, preamble f from a D, which is a subset of the complexes, to the complexes. So a complex function with A and D a limit point limit point of D, all right? Then f, well, let's just say this, f prime of A exists, which is just a quick way of me saying f is differentiable at A in the complex sense, if and only if there exists function phi from D to the complex numbers with the following two properties. One, phi continuous at A. Two, f of z minus f of A is equal to phi of z times z minus A for all z and d. Moreover, we find the limit as z goes to A of phi of z is equal to f prime of A. So not only is the function phi of z continuous, did I say continuous? Yeah, phi is continuous at A. And not only is it continuous at A, the value, basically, the value of phi at A is the derivative, right? And the name for this phi is the difference quotient function. The proof that that's the same as complex differentiability is straightforward, and I think I am going to forego it. It's on page 29, and it's very straightforward. What I want to instead do here is try to use this theorem of Caratheodory to prove another one of the derivative rules. Okay, so you know the product rule, right? Okay. So let's look at it. So we have, let's suppose f prime of A and g prime of A exist, all right? At A, an element of a domain D, right? And suppose D is the domain of both f and g, all right? Fine. So by Caratheodory, we know that we can write f of z minus f of A, right, is equal to some function which we'll call phi sub f, since it's for f, all right? Phi sub z times z minus A, right? But a more convenient way to think of that is what it really is that f of z is equal to f of A plus phi f of z times z minus A. So this is how I actually use Caratheodory when I'm doing proofs. I think, okay, well, what the Caratheodory does is it gives me a formula for f in terms of this difference quotient function, v. And likewise, g of z is g of A plus phi sub g of z times z minus A. So if I look at the product function, f of z, g of z, right, then I just multiply this and that. And what do I get? I get f of A, g of A, right, plus f of A times phi sub g of z plus phi sub f of z times g of A. And I factored out, well, fine, a little bit more, plus I'm doing a lot of algebra in my head at the moment. I hope you can forgive me for skipping some steps here, but this chalk writes awful slow. So this is an identity that is just obtained from multiplying the equations written right above it, all right? But I argue what this shows you is that the product of f and g is in fact complex differentiable. And more than that, its difference quotient function, right, its phi sub fg, if you will, is given precisely by what I've written in the big parentheses. See, this right here, yeah, this business right here is what I would call phi sub fg of z. Now, question, is that a continuous function? See, because in order to prove differentiability of the product function at A, I need to verify the two criteria for the theorem of Caratheodory, right? I need that phi of fg is continuous, and I need to be able to write, you know, fg of z minus fg of a as equal to phi fg of z times z minus a, right? The identity is already in front of us. So this manifestly gives you criteria 2 in Caratheodory's theorem, right? This is essentially the same as 2. Although I'm rewriting 2, I mean, technically I have to move minus that to the other side to make it match up with 2. Okay, fine.
But
Right.
it already exists for every z.
Right, and the other thing that I'm like glossing over here is this is technically the product function fg of z is by definition that, right? The product function fg of a is technically what I've got right there, right? Is this a continuous function?
Yeah.
It is, right? Because what you're looking at is a constant times a continuous function plus a continuous function times a constant plus the product of continuous functions times z minus a. Yes, those are all continuous at a, right? By the usual limit law arguments, which still hold in the complex limit. Limit law is also generalized to complex. So, hey, we've got criteria 1, criteria 2. Therefore, the derivative of f times g exists, and what is it equal to? So by theorem of Caratheodory, fg prime of a is equal to the limit as z goes to a of phi fg of z, right? And what is that equal to? I mean, look up here. What happens when you take the limit as z goes to a of the phi fg? Well, we get f of a. What's the limit as z goes to a of phi g of z? Well, that's by definition, I mean, by the theorem of Caratheodory, it's g prime of a. And then f prime of a from that one, yeah, times g of a, right? And then what happens, and I'll write it down, but plus the, yeah, plus 0, right? Because the limit, the last piece goes to, well, f prime of a, g prime of a, and then you're multiplying by the limit. I'll write it out, z goes to a of z minus a. But that, my friends, is exactly 0. So what do you have? You have the product rule. There it is. Oh, sadness, I just broke my chalk. Not just any chalk, precious Hagoromo chalk. It's truly sad when we break the Hagoromo chalk. So we can, but okay, now you're like, well, I could already approve this in the Calculus 1 style, right? Like sneaky addition by 0 and everything, but I tell you, there's really something beautiful about the theorem of Caratheodory and the ease with which you can prove things. Like, here's another theorem. If f prime of a exists, then f continuous at a. Proof. By Caratheodory, there exists phi such that f of z is equal to f of a plus phi of z times z minus a, right? Hence, the limit as z goes to a of f of z, what's equal to? But remember, the theorem of Caratheodory gives us that the limit as z goes to a of phi of z exists, and it's just f prime of a, right? So that limit exists, which means we can do the product rule for limits. And of course, we know z minus a goes to 0, right? As z goes to a. And so what are we left with? F of a, right? Which goes to show you that f is continuous at a. So differentiable implies continuous. But we will again see that continuous does not imply differentiable. But we need to, that's part of a larger discussion. But anyway, so just to summarize here, we can define the complex derivative in essentially the same way as we did in real analysis. I mean, not even real analysis, calculus 1, right? And we've got the derivative of a sum is the sum of the derivatives. We got the product rule. Guess what? We can also prove the quotient rule, right, and the chain rule. And there's a lot of things we can do, but here's one. I just want to challenge you with this as the sort of end point for today. What if you, this one's kind of hard. This one will motivate. How about, I mean, so you can do a lot of different, I mean, like we could go through the proofs of the polynomial ones, you know, and we'll start next class doing one of those probably, like one of the, you know, calculate the derivative of z squared or z cubed, you know, from the definition here. We can do that next class, right? That's not a big. You can either use the Caratheodory way or the limit quotient way. But how about this one? If you want to calculate, for example, f prime of, you know, z naught, what would it be? The limit as z goes to z naught, right, of e to the z minus e to the z naught over z minus z naught, yeah? Or make it simpler. Can you even hack your way through this? F prime of 0 should be the limit as z goes to 0, right, of e to the z minus 1 over z. This, okay, so if we knew L'Hopital's rule, right? Yeah. Then it seems like a piece of cake, but we have no such technology. So how exactly would you calculate the derivative of the exponential here? So look at it in terms of its real content? Yeah, I invite you to do that. Like, try to look at this in real notation. So this would be what, e to the x cosine y minus 1 plus I e to the x sine y, actually, when you write it out, over x plus iy. Remember, what we're looking at here is a limit of a function on the plane. This is a two-dimensional limit, right? So in order for that limit to exist, all possible path limits also have to agree. That's not at all obvious how that goes because as you're going to 0, y is going to 0, right? So this is going to, that's going to 1. So you got like, this is going to 0. That's going to 0. This is going to 0. 0 over 0. How do you resolve this limit? I mean, it's not, it's pretty, yeah, it's definitely indeterminate. How do you deal with that, like, directly? The good news is, next time we'll talk about what are called the Cauchy-Riemann equations, and we'll see that there's a way around it where we can just use a simple calculation to calculate the complex derivative. So So there's a great temptation for me here because there's a great nostalgia in just rehashing all of Calculus 1 and showing that all of the derivative rules can be derived here the same way as in Calculus 1, right?
Yeah.
But I think we should go on. Next time we will go on to the complex derivative, like the Cauchy-Riemann equations, as they're called.